These audio slides accompany the Expert Systems with Applications paper titled Smart Maintenance Decision Support Systems Based on Corporate Big Data Analytics. My name is Dan Bumblowskis. Here is the citation and link to the preprint version of the article. Operations and supply chain managers working in the area of maintenance, analytics, and modeling must consider what type of maintenance to do, when to do it, and at what cost. This is our primary motivation for the development of our smart maintenance decision support system. The specific case application that we explore in this article is based on a high voltage to medium voltage to low voltage electrical distribution grid as depicted in the illustration on the slide. You can see the hydro generation, the step-up transformers, and step-down to usage load at the end user level. More specifically, we look at high voltage circuit breakers and transformers. The picture here shows a high voltage substation class circuit breaker, and you can see in terms of some of the considerations here, we have a lot of internal and external factors that impact our maintenance decision making for these types of pieces of equipment. Historical maintenance process have been time-based and followed check sheets as shown on the left side here. And on the right side of the slide, we show more of a condition-based maintenance approach based on the number of actual operations seen by the device. The infamous adage, if it's not broke, don't fix it, applies in this sort of methodology. Here we present some examples of common integrated systems with dependency and interaction. So your general automotive applications, microelectronics, as well as power systems as shown in the illustration, where we again show a generation to load source and all of the different intermediaries between. The heart of the maintenance analytics model is a Markov decision process model based on various state and action combinations. We had failure incident rates from the field, transition rates to get units back into service, and the cost to repair units being the baseline for the dependency of components within the integrated electrical system. Here we have an illustration of the various state combinations of transformer and circuit breaker being online and offline, the actions between each one of those nodes and states, and the costs and transition rates to move between each one of the nodes or states. The Smart Maintenance Decision Support System itself makes use of a traditional software engineering layered architecture where we have the dependent component model that we just discussed, a marketing information system, the use of an analytical hierarchy process model, a full costing model, and an expert system in terms of decision making and support of components. The next two slides show a traditional maintenance sourcing model of going out to bid and having someone do a site inspection to look at equipment over a series of days, weeks, or months. And the subsequent slide shows the future state that we can achieve using the SMDSS. In addition to showing the future state here, we also have some diagnostic sensor data in terms of a snapshot of what one might expect to see. This diagram shows the architecture structure of the different component systems within the SMDSS architecture. Here we have a flowchart showing all of the user inputs leading into the output or deliverable being an end proposal for maintenance work based on the various system criteria and current condition states of the assets. Using a form of a Pareto analysis, we identified the top 8 failure modes for the equipment and then used an analytical hierarchy process model to prioritize maintenance across a fleet of equipment. Here is the AHP comparative judgment matrix. Subsequently, here is the element matrix for the cabinet component or failure mode. Finally, in the AHP process, we combine all of the different failure element matrices and combine them into one principle of composition matrix. The combined system requires these user inputs as the first step. We then run the aforementioned models to come up with an optimal maintenance policy. Our management decision makers can now use that optimal policy to drive their rationale for decision. The end deliverable or output is a proposal for service. Here we have some of the ongoing discussions and negotiations related to commercializing the system. Please don't hesitate to contact us if you have any questions. Here is the author contact information for the article.